Okay, in this video, we are going to look at this sequence and we'll find our explicit formula for this, and we'll see if this right here is increasing or not. And in the end, we'll see if this right here converges or not. Here we go. First of all, look at the top, 3, 6, 9, 12, and 15. And of course, keep on going. And of course, right here, we just keep adding 3 on the top. Therefore, we have a arithmetic sequence on the top. And on the bottom though, from 7 to 14, from 14 to 28, notice that every time we just multiply by 2. So that's a geometry sequence right here. And the strategy is, let's just look at the formula for the top right here first. Well, on the top is arithmetic. This is what you can do. You can just write down a1 plus n minus 1 times the common difference. And you can use this to set up for arithmetic sequence. And of course, a1 is 3. We'll just put that down right here. And this is equal to that. And then we have plus n minus 1 times d. D is also 3. The 3 in red, like multiplying, right? So multiply by 3. And of course, right here, we can just work this out real quick. This is 3 plus distribute, we get 3n minus 3. Of course, 3 minus 3 is 0. So in the end, we just get 3n like this. And a quicker way to do the arithmetic sequence is that you can just notice it has to be n to the first power for the arithmetic sequence. And the coefficient, it's always going to be the common difference because d times the common difference, d times the n, so that's the common difference times n. And in the end, once you put this down, you just have to ask yourself, do you have to add anything or subtract anything so that you can actually produce the first term when n starts with 1? In this case, we don't need to, right? When n is 1, 3 times 1 is just 3, so we are done. So that's the formula for the top. And then we are just going to find the formula for the bottom. And we start with 7, 14, 28. That's a geometry sequence. So to do that, we're just going to use a1 times r raised to the n minus 1 power. And keep in mind, all these questions, we start with n equals 1. And of course, for this right now, we'll just put everything in. a1 is 7, and then r is 2. And then we just raise that to the n minus 1 power, like this. That's pretty much it. So all in all, we just have to divide this and that. an is equal to 3n over this, 7 times 2 raised to the n minus 1 power, like that. So that's pretty much it. Well, you can simplify this a little bit because we have 2 to this power. We can write this down as 2 to the n times 2 to the negative 1. This right here stays on the bottom, but 2 to the negative 1, we can take that and bring that to the top. And when you do that, we will end up 2 right here to the first power, and then of course you have the 3n, and of course the rest, 7 times 2 to the nth power right here. And all in all, we can of course simplify this. Finally, we get an equals 2 to the first times 3, of course, that's 6n over 7, 2 to the nth power, like that. Of course, put dot or parentheses. I'll put down a parentheses right here, otherwise it looks like 72, which is of course not. All right, so that's pretty much the idea for this. So that's the explicit formula for that. Now, moving on to if this converges or not. Well, I mean, if this increasing or not, let's do that first, right? If you look at this right here, from 7 over 3, 6 over 14, 9 over 28, in fact, every value is getting smaller and smaller, right? This fraction is actually smaller than the previous one. So here's my claim. I claim that an is actually decreasing. And of course, once I claim this, I will have to show you. And to show this, technically, you will have to do some algebraic work or maybe use some calculus to argue that. And I will just show, this is the proof, right? It's a real quick proof for that. When you are trying to show an sequence is decreasing, all we have to do is a sub n plus 1, meaning the next term. I'm trying to show the next term has to be less than or equal to the current term. And of course, right here, you can just put down less than, but it doesn't really matter, less than or equal to. Yeah. Okay, so that's pretty much the idea. And now this works just like functions. when you have a sub n plus 1, all we do is just put a sub n plus 1 into this n and that n, and then just pretty much work that out. So we get this 6 times n plus 1, and divided by 7 times 2 to the n plus 1 power, like that. And by the way, I don't know if this is true or not. I will just put on a little question mark. And this right here is actually, we're trying to show if this is true for n is greater than or equal to 1. Because again, n starts with 1, and then 2, 3, 4, and so on. Anyway, continue, just go ahead and check. An is just exactly that. So just put that down. 6n over that. So that's pretty much how sequence works. Right? So we have the 7 times 2 to the nth power like this. Alright, maybe we don't need the dot, doesn't really matter. We just have to check this inequality. The good thing is that everybody is positive, so we can just kind of do some usual algebra without really worry about the inequality symbol too much. Alright, so perhaps this is what we can do. This right here, of course, we can distribute. We get 6n plus 6 over, this is 7 times. Let's rewrite this part as 2 to the n times 2 to the first, and are we going to get this being less than or equal to 6n over 7 times 2 to the n? Well, as we can see, we can just multiply both sides by this denominator. Again, the denominators are positive, so we can just multiply, and we don't have to worry about the inequality symbol. We just multiply by 7 times 2 to the n times 2 to the 1. Or you can also cross multiply. Pretty sure that's a similar idea. Anyway, when we do this times that, this is gone. We have the top, which is 6n plus 6. Do we actually get this less than or equal to? Okay, 7 and that cancel, this and that cancel, but we'll have to do 2 times that, which is 12n. And so this right here is 12, right? 2 times the n, so it's 12. The 2 times the 6n is 12n. And now we can just do more algebras. Minus 6n on both sides. We have 6 is less than or equal to n. And then we just, minus 6n on both sides. So 6 is less than or equal to n. Well, of course, divide both sides by 6. Read it backwards, n is bigger than or equal to 1. And that's exactly what we have. So this right here is true. So in fact, after the first term, it will be decreasing. That's the beauty of that. So an actually is decreasing, right? So you can just make your statement and you prove your statement, right? That's the claim, right? You make your claim. All right, so that's all. And the last thing is that we'll see if this right here converges or not. I will say this. We are going to check the limit as n goes to infinity of an, which is that, namely 6n over 7 times 2 to the n, like this. Let's put on parentheses again. Okay, so here's the deal. On the top, we have a power function, n to the first power, but on the bottom, power sequence, n to the first power. And then this right here is technically an exponential sequence, right, 2 to the n. And the idea is that based on the list, we know that the top is much smaller than the bottom. So in fact, this right here will give you 0, right? This right here will be giving you 0. Why? Because again, right here, you can just say by the list. N to the p's power is so much smaller than b to the nth power, right? And you can just say that's by the list. When you divide, the limit will be 0. So in another word, we can finally say an does converge. And we know that this right here, it actually converges to 0. So that's pretty much the idea. And this is what we do. That 1, 2, 3. Okay, let's take a look at the sequence and notice that we have all the ones on the top. So that's very nice. And on the bottom, we have 3, 8, 15, 24, 35, and so on, so on, so on. Notice that if we look at this as plus 5, plus 7, plus 9, plus 11, okay, that's good because the next one will be plus 30 on the bottom. And notice that though, this right here is actually not arithmetic sequence because the difference is not the same. In fact, this is a quadratic difference because from here to here is 5, from here to here is 7, right? That's the first level difference. If you look at the second level difference, is plus 2, plus 2, plus 2. That's how we know from here to here, it will be plus 13. Okay, you have a quadratic sequence, but in this case, here, it's actually easier to not use any of the quadratic sequence formula for this. Because if you look at the 3 as 1 times 3, if you look at the 8 as 2 times 4, if you look at the 15 as 3 times 5, if you look at the 24 as 4 times 6, and 35 is 5 times 7. Well, notice, this right here is the first term, which is the 1 right here, the second term, third term, fourth term, and then the fifth term. And this number that we multiply is just 2 more than the term that we are talking about, right? So right here, we can see it pretty clearly now. An is equal to 1 on the top, so that's very nice, over n right here, and then we multiply by n plus 2, like this. So here is the explicit formula for that. And now let's talk about if this is increasing or decreasing, or maybe not. As you can see, we have 1s on the top, right? So the denominator is also getting bigger and bigger, so we know this is a decreasing sequence. But to show that, I will tell you, we are going to claim an is decreasing. Well, let's check, right? This little proof or check, up to you however you want to say it. Well, the definition is that an plus 1, meaning the next term, has to be smaller than or equal to the current term, which is an. And to do this, of course, you can just put this down. This is 1 over n, which is now the n plus 1. You have to put this right here for this n and that n. So we get n plus 1 times n plus 1 and plus 2. Right? N plus 1 and then plus 2 like this. And the truth is, I am not really sure yet, so put on question mark, we have to do the check, right? And this is an, which is just that. And that's 1 over n times n plus 2. Like this. And we're trying to see if this is true or not for n is greater than or equal to 1, because in our situation, n starts with 1. Now, we can just do some algebra, and perhaps we can just cross multiply, because everybody is positive. Cross multiply is pretty easy, and we don't have to worry about switching the inequality symbol. Now, let me just move this to there, or move this to there. So we get, do we get n times, let me just put this down like that. We get n times n plus 2. Is this less than or equal to this times that, which is n plus 1 times n plus 3 pretty much? Now, is this true? Well, just keep doing the algebra. This right here is n squared plus 2n. And do we get less than or equal to? Multiply this out, we get n squared plus 4n altogether, right? The 3n and then 1 more n, so plus 4n. And in the end, we have the plus 3. And just keep on doing. You see, we can get rid of the n squared on both sides, and we can minus the 2n on both sides. So we have 2n right here, right? After we minus the 2n on both sides. And we can also bring the 3 to the other side, so we have the minus 3 right here. Well, it's pretty clear. If you really want to see it, you can divide both sides by 2. So it depends on how much your teacher wants you to show, but if you do it this way, it should be pretty clear. This is true because n is bigger than or equal to 1. So this right here is true. So that means an is decreasing. You can just do some algebra like this. So that's it. Now, we'll see if this converges or not. So here we go. We are going to check. The limit as n goes to infinity of an, and we'll just do this, which is the limit as n goes to infinity of 1 over n plus 2, n times n plus 2. And notice that the bottom is going to be infinity, so of course 1 over infinity we get 0. So this means an does converge and converges to 0. So yeah, this is really easy, just 5, 7 all the way. But how can we write an explicit formula for this? Well, notice that we add 2 here, and then we subtract 2, and then we add 2 again, and we subtract 2, and so on, so on, so on. This right here, let me tell you guys how to do it real fast. All we have to do is, let me just write down an first, of course. All we have to do is, we are going to find the middle of 5 and 7. Of course, that would be 6. right? And what we are going to do is, 6. When you subtract 1, you get 5. When you add 1, you get 7. That's how we find the middle. And all we have to do is just plus. Remember, 1, -1, or -1, 1, and all that. The base is -1 raised to the nth power. That's it. And be sure you just kind of pay attention to if you need -1 to the nth power or -1 to the n plus 1 or minus 1 power like this. Check this out. We want to start at 5. When n is 1, we have 6 plus -1 to the first power, so we have 5. When n is 2, right here, this is going to be a positive 1. 6 plus 1, of course, is 7. And then the rest is pretty much the same. So that's pretty much how you can get this real fast. So here is the formula for an. Well, this right here just keep up and down, up and down, up and down, right? So unfortunately, this right here, an is not increasing, it's not decreasing. So I'll just say is either increasing or decreasing, right? So it's none. So nothing. And then in the end, we'll just check the limit as n goes to infinity of an. Well, of course, right here, this is the same as saying the limit as n goes to infinity of this expression, 6 plus -1 to the nth power. And this is very similar to the sine cosine situation. You just go like this. It has no limit because this is like we cannot make its mind, so we cannot really see if this is approaching to anything or not. This right here, it will just tell you does not exist. I will just say, well, it's equal to does not exist. I don't know how much sense it makes, but I will put it down anyway. Does not exist. So I will just tell you, well, not that. So in the end, we'll just say an diverges. Yeah, because you don't have a limit right here. So an diverges. Okay, in this video, let's take a look at this sequence. And first of all, we're going to find an explicit formula for this. Well, let's write down an. This right here is actually not that bad because we see that we have sine 1, and then here we have 2 sine of 1 over 2, and then this one is 3 sine of 1 over 3. And the next one, of course, you see that 4 and 4 right here. Therefore, once we get to the nth term, we have n times sine of 1 over n. That's it. And of course, let's close the parentheses. Here is the formula. Now, we're going to see if an is increasing or decreasing or maybe neither. But this right here, it's actually pretty hard to deal with if you use the an plus 1 if you want to show that compared to like an, because we have the sign right here, right? So how else you can do it is just use the graph for it. Well, to do that, let me just put this down right here for you guys. We are going to graph the function version of that. It's easier to do it on your calculator this way. So let's take a look at the graph of f of x being x times sine of 1 over x. And whatever you can say about the function right here, like if it's increasing or if it's decreasing, you can say the same thing right here. And because you will see the picture will actually help us out. Well, when you graph this, you're going to get something really crazy here. Okay, so just kind of graph it on your own, and then it's going to get like this. So it's going to be behaving nicely after a certain point. And the graph of an is just that you are just going to put in when n is equal to 1, 2, 3, and so on. Based on the graph, you'll see you have this point here, and this point here, and so on. In fact, this right here is increasing, but we do see this right here has a horizontal asymptote. Therefore, it does have a limit. Therefore, an does converge. But the second question right here is just that if an is increasing or not, and in this case, I'll say an is increasing. Why? By looking at the graph. And of course, you have to provide the graph, right? And for the third one, we are going to see if an converges or not. Of course, we can use the graph, but let me show you guys how we can do it. Well, not algebraically, just do it by doing some actual computations. Anyway, we are going to check the limit as n goes to infinity of an. And of course, this right here is the limit as n goes to infinity. An is that n times sine of 1 over n. Notice this right here is an infinity times 0 situation. So we cannot draw any conclusion yet. What we can do is just bring this n down, and we are going to get the limit as n goes to infinity of sine of 1 over n divided by, once you bring this down, we will have 1 over n like this. And notice, this and that are the same. That's good, because when n goes to infinity, this and that, of course, they both approach 0. So we can quote the limit for this right here. And to do so, this is what I would prefer you guys to do. You are going to write this down. You are going to say, like do a substitution, let theta equal to 1 over n. And check this out. When n was going toward infinity, well, theta will now go to 0 because 1 over infinity is 0. So I'll just say theta goes to 0. And of course, the inside is theta here over theta here. And of course, this is not like integral. You don't have the d theta here, okay? So don't worry about that. But anyway, this right here is equal to 1. And if you want to give a little reason, this is by the limit that I discussed with you guys before, right? This and that input are the same, and then if the input is approaching 0, then we are pretty much done. So I will tell you that an does converge, and it converges to 1 right here. So this right here is very good. It's pretty easy to describe what's going on, right? Because the first one we have square root of 2. The next one we have square root of 2. And also the square root of 2 inside. And the next one you have this. You have 3 2's, but you have 3 square roots. And 2 of them are inside of the big one. And so on, so on, so on. And of course, you can imagine the next one is square root and then with 2 and then square root of 2. And then all together you have 6 2's. And then open the 6 square roots and all that. How can we write a formula for this though, like mathematically? Well, as always, I do tell you to my students, in calculus, we almost always look at square root as the 1/2 power. So let's look at this as the 1/2 power. Right here, this is the same as saying 2 to the 1/2 power, like this, just that, And then the next one, it's going to be, okay, this right here is 2 to the 1/2 power, right? Because this 2 is the square root of 2 only. But when we have the square root inside of the square root, this right here is a 1/2 power inside of another 1/2 power. In another word, we get 1 over 4th power because we multiply the powers. So this right here will give us 2 to the 1 over 4th power. And then next, if you look at this right here, same thing. This right here will be 2 to the 1/2 power. But this right here is the same as that situation. So we get this 2 being to the 1 over 4th power. However, here we have one more 2, Right here. This is inside of a square root inside of another one. So we have to deal with this as 2 to the 1/2 power, to the 1/2 power, to the 1/2 power. Multiply the powers, we get 1 over 8. So 2 to the 1 over 8 power. And of course, you guys can imagine, the next one is going to be 2 to the 1/2 times 2 to the 1 over 4 times 2 to the 1 over 8, and then times 2 to the 1 over 16 and so on. So I think this right here should be enough. Well, let's just add up the fractions because now we're just having multiplication situation, right? Thankfully, it's just multiplication, so it's not that bad. Anyway, let me see if I can add the fractions. This is 2 to the 1/2 power. 1/2 plus 1 over 4 is 3 over 4. So this is 2 to the 3 over 4th power. This right here, just get you a little common denominator, you get 7 over 8. So 2 to the 7 over 8. And then the next one is going to be 2 to the, well, it's going to be 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, which is going to be 15 over 16. And so on, so on, so on, right? So if you look at this right here, everybody has base 2. That's good. But how can we describe this though? Again, n starts with 1. You notice the denominator here. This is 2, 4, 8, 16. In another word, they are powers of 2. So now we can pretty much write a formula. base is 2, and then the power has a denominator 2 to the n, like that. And the top is actually just 1 less than the denominator. So once we figured out the 2 to the n, on the top is just 2 to the n minus 1. So that's it. It's a pretty crazy looking expression. 2 for the base raised to the 2 to the n minus 1 over 2 to the n's power. Just like that. Very cool. Now, does this increase or decrease? Is this an increasing sequence or decreasing sequence? Well, you can use a calculator or whatsoever, up to you. But as you can see, every time we have more things multiplying. So this right here, it's pretty clear that we have an increasing sequence. So an is increasing. And of course, you can do the computational work as well, but I will leave that to you guys. All you have to show is the powers. The powers are getting bigger. Of course, the whole thing are getting bigger as well. Well, does an converge? An does converge. I'll show you. An does converge. And to do so, let me just put down on the side, we will have to check the limit as n goes to infinity of an, which is 2 to the n minus 1 over 2 to the n. Ignore the base for now. Just pay attention to this power here, because you have 2 to the n and also 2 to the n here. The minus 1 doesn't matter. It's just pretty much worry about the dominating part, right? And you will see it's just 1. And in the end, you get the limit as n goes to infinity of 2 raised to the first power. So yes, the answer is just 2. So in another word, an converges to 2. That's it.